Under the cover of darkness, the world lies hidden from view. Without light, I've no idea what lies beyond my immediate surroundings. I'm closed in, enveloped on all sides by the unknown. For much of human history, when the sun went down and the dark set in, we were at the mercy of the night. But over the centuries, we've developed our own sources of illumination. We've lit our homes, our streets, our cities, and in doing so, we've banished the darkness into the shadows. And just as we've used light to illuminate our world, the more we've discovered about light's properties, the more of the universe it's shown us. We've seen into the depths of space and back to the beginning of time. But as we've looked deeper, we've come to realize how little we've seen. And that the cosmos's greatest mysteries remain hidden in the dark. Light and dark is essentially the story of everything we know and everything we don't know about our universe. And it all begins with light. It's such an integral part of the way we perceive the world, it's easy to take it for granted. But for centuries, understanding what light really is has been one of science's most enduring questions. The first steps towards understanding the properties of light were made in the 3rd century BC by the renowned Greek mathematician Euclid. And he did it by thinking about something so obvious that most of us don't give it any thought at all. Placing the tiny chair very close to the camera produces a large image on the retina. And because we're not used to seeing tiny chairs in everyday life, our brains are tricked into thinking it's a normal-sized chair in the middle of the room. And the reason this illusion works at all is because to judge distances, our brains rely on a simple fact. The further away things are, the smaller they appear to the eye. And it was by focusing on exactly why distant objects could appear the same size as much smaller ones closer up that led Euclid to discover one of light's most fundamental properties. Obviously, the London eye is much bigger than my fingers, I know that. And yet, to me, they look the same size. So how do we explain this? Well, Euclid came up with an elegant solution. For my finger to appear at the top of the wheel, my eye, my finger, and the top of the wheel must all lie on the same line. But Euclid's insight didn't just explain the tricks of perspective. It revealed a basic truth about light itself. Euclid had discovered that light travels in straight lines. Realizing how it travels marks the beginning of our scientific understanding of light. And it also meant that if we could divert it from its straight line path, we could change the way we see the world. But that leap wouldn't happen for another 2,000 years. It was eventually made in Renaissance Italy by one of the founding fathers of modern science. In the summer of 1609, Galileo Galilei made the short but fateful journey from his home in Padua to Venice, capital of the Venetian Republic. Galileo had flame-red hair, a full beard, and was well known for his love of fine wines and generous hospitality, and also for his anti-establishment views. By this time, he'd also built up a reputation as a natural philosopher and mathematician, and he was regarded as a valuable asset to the Venetian Republic. But although, as a professor, he had a regular income, Galileo was never far from financial troubles. When his father died in 1591, Galileo, the eldest of 4 surviving siblings, became head of the household and effectively took on responsibility for supporting his brother, a poor itinerant musician, and for paying his sister's dowries. By the time he came to Venice, he still owed a significant amount of money to his 2 brothers-in-law, and so was always on the lookout for a money-making scheme. And that summer, Venice was abuzz with rumors of a device that appeared to do the impossible. A Dutch spyglass that could bring distant objects closer. It was just the opportunity Galileo was looking for. Back in the 17th century, the spyglass was cutting-edge technology, and details of how it worked were a closely guarded secret. All Galileo knew was that it consisted of 2 lenses arranged in a tube. And so when he developed his own, he kept it very secret as well. But we do know from a shopping list that he got his glass from the small island of Murano out in the lagoon. And because no tools existed, he had to improvise, for instance, buying an artillery ball to grind the curved surfaces of the lenses. It had been known since the first spectacles were produced in the middle of the 13th century that glass had the strange property of bending light. But unlike spectacles, the spyglass, an early telescope, required a combination of lenses in a very specific arrangement. This is how Galileo's telescope works. Rays of light come in from a distant object, so they're almost parallel, where they meet his first lens. This is the objective lens, and it's plano-convex, which means it's flat on one side and curved on the other. It's the sort of lens used to treat long-sightedness. What it does is bend the rays of light towards each other so that they would meet at a point. But before this focal point, Galileo places his second lens, the ocular lens, which is plano-concave. And this bends the rays of light back out again so that they emerge parallel where they enter the eye. And then the eye's lens focuses them on the retina. Now, the magnification of a telescope depends on the ratio of the focal lengths of the 2 lenses, the distances f1 and f2. The difficulty for Galileo was grinding down the convex surface of his objective lens to make it as shallow as possible in order to maximize the length f1, because the longer he could make that, the greater the magnification of his telescope. Produced in just a few weeks, Galileo's telescope had a magnification of 8 times and was far more powerful than the original spyglass. All he needed to do now was cash in on his new invention. Ever the showman, on the 21st of August, 1609, Galileo climbed one of the city's bell towers. Obviously, he'd have used the stairs. At the top, in front of an assembled group of Venetian noblemen and senators, Galileo demonstrated his telescope. It was a sensation. Using it, the Venetians would be able to see approaching ships 2 hours earlier than with the naked eye. The military and economic advantage of knowing who was sailing over the horizon was lost on no one watching that day. 3 days later, as a grand gesture, Galileo presented his telescope to the Duke as a gift. In return, he was guaranteed his job for life at double his salary. With his finances now secure, Galileo went on to develop a more powerful telescope. And with it, used the ability to bend light to change our perspective on the cosmos. This is the book Galileo published in 1610. It's called Sidereus Nuncius, which in Latin means the starry messenger. In it, he recorded his first observations of the night sky, the first anyone had ever made using anything other than the naked eye. Today, it's hard to imagine how anything contained in this little book was controversial. But you have to remember that back when it was written, the nature of the heavens was thought to be knowable only to God, and the Earth was considered to be at the center of the universe. These are his drawings of the moon. Since ancient times, all heavenly bodies were thought to be perfect spheres, but with his telescope, Galileo saw texture in the surface of the moon. Deep craters and mountains that, from the shadows they cast across the lunar surface, he estimated to be some 6 kilometers tall. As well as showing the heavens to be imperfect, his telescope began to uncover their true extent, revealing 10 times more stars than are visible to the naked eye. And in the final chapters, Galileo reports the discovery of 4 stars that appear to form a straight line near the planet Jupiter. His drawings show how their positions change from night to night. Although they moved, they always did so along the same straight line, and from that, Galileo deduced that they had to be orbiting Jupiter. They weren't stars at all. They were moons. Through his telescope, Galileo had seen evidence that overturned the accepted dogma that the Earth was the fulcrum about which everything in the universe revolved. Seeing moons in orbit around Jupiter meant that not everything went round the Earth. So, far from being the center of the universe, the Earth was just another planet. telescope had allowed Galileo to glimpse the true nature of the cosmos and our place within it. But this way of manipulating light had another powerful application, one that would allow us to see into another world. In 17th century London, one of the most prominent scientists of the age was using lenses in a very different way. Robert Hooke had taken the basic principle of the telescope and used it to build a microscope.
Galileo uses the telescope to discover a new world in the heavens, and Hooke uses the microscope to discover a new world in the very, very small. But there's a difference, because what Galileo had presented was a world that was bigger and more plentiful, but it was a world that people were at least vaguely familiar with, because you can look up in the sky and see the stars. Whereas the world that Hooke presented was really something spectacular and new. It was a world inside the tiniest particles of matter that no one had ever imagined to be there before. People didn't even realize that there was a microscopic world there to reveal.
Hooke trained his microscope on a huge range of materials and living things. But it was his drawings of the exquisite detail he saw in the bodies of insects that would become famous.
So up here you can see a human flea, Pulex irritans. It's a very tiny creature. And then here we've got the plate from Micrographia, which is a huge image of the flea that Hooke produced. And it's really something spectacular. And this would have folded out in the book, so it was really very large. Some people said it was as big as a cat.
It's a work of art, really. I mean, there's just so much intricate detail in there.
It is, and there was nothing like it before Hooke. They really were unprecedented. And the shading and the quality of the images is just superb.
And it's accurate. I mean, it's...
It is. It's absolutely accurate. I was looking yesterday at images of photographs of the flea, and there's really, actually made with an electron microscope, and there's really nothing to choose between Hooke and the current images. This is an image of the compound eye of a fly, which Hooke shows in amazing detail for the first time. And this is an image of the foot of a fly. Hooke shows you the foot has little spikes in it that allow it to clasp into the pores on a surface.
Now, this image looks less interesting, less intricate than the others.
Well, it doesn't look terribly interesting, but actually it's really quite a profound picture, because what Hooke is looking at here is a very thin slice of cork, which he cut with a penknife, and he's looking at the little individual components that make it up. And he calls them pores, and then he calls them caverns, he calls them boxes, and then he calls them cells. And cell, of course, is the term that stuck. These are the little constituent parts, not just of cork, but of all living things. And so it's actually a profoundly important discovery and a name that has become standard in biology.
Using glass to bend light revealed our true place in the universe. And the intricate architecture of the microscopic world. The more we looked, the more we saw. With each new insight into the nature of light came a fresh understanding of the cosmos. And the next discovery would take us far further and enable us to read the story of the stars. And it began with something Hooke had glimpsed through his microscope.
This is Robert Hooke's book, The Micrographia, published in 1664, 350 years ago. It's full of his famous diagrams. Here's his picture of the flea. It's incredible seeing it in its original form. It really is the size of a cat. These images really captured the public imagination and they made the book a sensation. But for me, the Micrographia is about much more than that. The chapter that interests me as a physicist is one that contains hardly any images at all. And it's this one here, of the colours observable in Muscovy glass and other thin bodies. Here, Hooke describes the iridescent patterns of rainbow colours he sees through his microscope as light passes through thin materials, like soap bubbles and Muscovy glass, a silicate mineral that's made up of lots of thin layers. At the time, it was thought that white light, like sunlight, was pure, that it came directly from God. And so Hooke concluded that the colours he was seeing must have somehow been added to the light, that they were effectively created as the light passed through the materials.
But Hooke's theory about coloured light was about to be challenged by his greatest rival. Isaac Newton is one of the world's most revered scientists. Best known for his theory of universal gravitation. And just like his laws of gravity, Newton's discoveries about the nature of light are among his most celebrated achievements. But the story of how that work began is much less familiar. And this time, there was no fruit involved.
This is Stourbridge Common, a sleepy riverside meadow on the banks of the River Cam. But when Newton visited in 1664, it would have been very different. For over 700 years, every September, this place would be transformed into what was, at its height, the largest fair in Europe. For several weeks each year, people would descend on the common for an annual festival of commerce and debauchery. This whole common would have been packed with makeshift stalls. Farming produce, brandy houses, goldsmiths, silk merchants. There'd have been slack rope dancing, puppet shows, music, temptations of every kind, packed into row upon row of wooden booths and tents. Stourbridge Fair was a place you could buy anything you could imagine. But when Newton came here, it's said he bought just one thing, a prism.
He bought it because it performed the same magic Hooke had seen with his microscope.